This project is to limit memory usage per Alluxio client session. I would like to introduce a few terms before we get on to the actual project. So when I say Alluxio client, it is nothing but the Spark or MapReduce or any kind of application that is running on top of Alluxio. And Alluxio is going to be the memory centric distributed storage here, and it uses HDFS or Ceph for the lineage. We are using HDFS, and the configuration that we are currently going to test is a setup where there is one worker running and it is also the master, and we have three layers configured: memory, SSD and HDD. The memory is of 1 GB capacity, SSD is of 1 GB, and hard disk is of 5 GB. Downloaded Spark code and Alluxio code and built it both on this setup. Here is the setup. I have compiled the Spark code. As you can see, the build is successful. Here I have formatted the file, started the Alluxio services. This is the configuration file that is set up on the master. The master is the worker here. As you can see, the allocator class is set to myAllocator. Evictor class is set to myEvictor. The block size is 2 MB, and then the session limit is set to 32 MB. This is equivalent of 32 MB in bytes, and the location policy is set to my location policy. Once the system is formatted, you can see that the memory here is 1 GB, SSD is of 2 GB capacity, and HDD is of capacity 5 GB, and each is 100% free. We can see that there are no files in the memory, and the file system also does not contain any files. I've saved a file. This is a MOV file. I'm moving it from local file system to Alluxio memory. So this is the command. It copied the file. So as you can see that only 52, the total size is 60.70 MB and the block size is 2 MB. So it has saved just 52% in the memory and rest of it is saved in the SSD. This is not this is an MOV file, so there is no reader to read it. That's why you see all these question marks. We can see that each block size is set to 2 MB. I've created a file using copy from local file to Alluxio. Its size is 855 KB, it is less than 32 MB, and in that session it put the entire file into memory. So you can see that 100% of the file is in memory. This is the command I use. So each is a session over here. What I'm going to do next is to start a Spark sessions. I'm going to start about 4 sessions, and I'll access this file from the Spark session and try to write it into the Alluxio. Let's see what happens. The Spark shell in each session. I have 4 sessions here, so I'm going to start simultaneously in all the sessions. Each one is going to be an Alluxio client session. So we can see that once I run it, 4 Spark session IDs are going to be generated. I am just going to read the file out in each session. Run this command to read the text file out that's in the Alluxio. So each one is going to frame the RDD, but it won't save anything on the Alluxio because the actual operation is not done at this stage. So t.count is the command to read the number of words for that file. So I'm going to read the number of words. This is when the client will create a session and register with the master and then read or write with the worker. So I'll just execute it at all the sessions. So we can see that the output is same in all the terminals, and you can see that the session ID that gets generated is different in each case, and the session ID that gets generated is the client information. This is the process ID and this is the mission information. So this is the hash code of the process ID and the mission. I'm running a command to save the out.txt as a different file, O1, O2, O3, O4 in each of the prompt. So it has succeeded. So I have saved the files. Now you can see each session ID that gets displayed when this file gets saved. So you can see the 4 session IDs over here as highlighted. Now I would like to show the same how we store the information in the session manager. So the log should also print this. I've searched for that. Now let me look for 10 the first session ID 1052 begins with 1052 and you can see 1052047888. This is consumed 87821 bytes and there is 4 similar sessions which is consumed same bytes because I saved the same file, and each of the session IDs would remain the same. I'm just copying it in order to verify it out. So I'll just open a I have copied the contents to this, so you can see that 13741. So first let me find that session for you. 105278. So you can see that consumed 87521 bytes. So similarly we can get the session ID from this session. This information what you see is saved in the worker.log or on the worker end. So this information is saved in the worker session manager. I have opened the 4 terminals again, so I'm going to read a file which is about 60 MB. So I'm just going to read it in this variable in all these sessions, and I will save this file as I'll save this file in first session. So you can see that this is about 64 MB getting written, so it's completed. Let's look at what is the percentage that is written to the memory. We can see that as and when I keep adding more and more files, it does not add to the memory, instead it gets added to the SSD. So I'm just going to save that file again. It was 123. The session limit is reached, so it just saves the file to SSD instead of saving it in memory. So even though there is enough space in the RAM, but it doesn't save to the RAM, it is moved to the SSD. Let me show it again. So you can see that it increased to 431 MB. The RAM still remains at the same size. This is 178 MB. So as and when we write the files, it keeps increasing. So what I'm going to do is I'm going to write a few more files to it. So as to just verify that the SSD is getting filled now, so that I can spill into HDD. But before that, I just want to see what happened to the blocks. So as you can see that the block size each is 2 MB. So you can see that it's not in memory. There's nothing in memory right now. So everything is pulled to the SSD. At the same time, we should be able to view from logs that session ID. So if I look at the session ID, I see that the table is printed where the maximum is reached. That's why it's spilling out to SSD. And next, when the SSD is full, it will start spilling to HDD. So that would be the behavior of the allocator. I would like to show the location policy here. If you look at the user.log, for each write operation, the client requests tries to find out which worker it can use for writing the next block. So if you look at this, my location policy is provided in the environment.sh, and when this gets invoked, it picks up the worker to write the block. What we are doing here is that for a session we return the same worker for writing all the blocks. So you can see that for all the blocks that is written, the same worker is picked up. In case, this will be very useful in cases where you have multiple workers and the client tries to write to the worker. Having only one worker per session avoids syncing of the session information to the master and to the other workers. So the whole purpose of adding the location policy is to have one worker for the entire session. There are two portions in allocator. One is that when the file size or the session limit exceeds greater than 32 MB, it tries to allocate it on SSD, or when it is less than 32 MB, it goes to the RAM. But at the same time, it will also invoke or request for the free space, which goes into the free space queue, and it requests for the number of bytes. For example, it how many bytes you need in the each tier so that it can do some eviction. So the previous demo what was shown was by disabling the free space. Now I have enabled the free space. As you can see the code, the free space thread gets called, so it checks whether the a space reserver is enabled or not. If it is not, it's not an asynchronous eviction. This is a synchronous eviction because you call it when you're committing the block. If you detect that the committed session memory has exceeded the session limit, then you try to invoke the free space API. So you can see in the logs that the free space API is invoked, and as you can see here, it starts messing up with the map where it even exceeds the limit of the size of a session. That's because when it's freeing the space, it frees up space for that particular session. Yes, it detects from the map, but at the same time, there is a problem in finding the directory where it has to move the blocks to. So it always puts it in the RAM. So immaterial of what the session ID is or what is the limit of the session ID, it cannot find any other directory if RAM has at least a little space. A little, when I mean at least the space of a block to be inserted. So in such cases, it starts failing. I can show an example. When I try to write a file which is of greater size, and at the same time when it tries to free the space, it starts failing. It won't be able to find the candidate where or the directory where it can move blocks to. So we need to fix this in order to propagate the session information everywhere. Yes, it is propagated everywhere. Still, there is some point that needs to be integrated with the session ID to free only blocks that belongs to the session ID and find room to put that block only in the next tier and not in the RAM. That's why we run into the exception, and we are still working on it. There are a few other things that we have mentioned it in the future enhancement. For example, when you restart the worker, it's not fault tolerant, so we don't say the session map anywhere. So when the worker gets restarted, all the session information is lost. So we want to make it fault tolerant and fix this evictor so that it works according to the plan that we came up with. This is our end of the demo, and I think we have showcased all the features that we